what you get is some kind of a lines. What has no lines of English? Okay.
101.
101 table. So multiplication table. What you get is a multiplication table without the one row and the one column and the one row. So all elements in this table are non-prime, obviously, because every element is at least the product of two different numbers. So when you have two vectors running from 2 to 99 or 100, and you create an outer product of these two vectors, you get a table containing only non-prime numbers. Way more non-prime numbers as needed, but at least all the non-prime numbers between 2 and 100. The idea is, okay, I created such a table and use this table to select from my original vector ranging from 2 to 100 all elements which are not in this table. These must be the prime elements. And that's the trick of this prime list word. Prime list generates a vector running from 2 to, in this example, 100, creates four versions of this using 3 dots, and then we push a multiplication operator on the stack and apply the word outer, which performs an outer whatever, in this case product. We could have generated out the sum or whatever. The result of this is the table I mentioned. Then I swap the table and one of the copies of this original vector, perform the in operation. This yields a selection vector consisting of zeros and ones for every element of the vector which was in the matrix or not in the matrix. I invert this vector, apply the select operation, and voila, what I get is a vector of all prime numbers from 2 and to 100. Okay, just a few more examples without detailed explanations. You can use the built-in operations of 5 to create quite simply ASCII graphics. Okay, that's not too impressive, but it may be impressive if you see how short the source code for this is. Try this in Fortran 2000. Our matrix vector multiplication. In contrast to APL, we don't have a built-in matrix vector multiplication operation. This is because it's so incredibly simple to implement it in 5. What we need is an inner sum operator, which can be applied element-wise on a more dimensional array, and we need an own operator NV star for matrix vector multiplication. And it really works. Multiplying this matrix on the left side by the vector on the right side really yields 68, 1, 6, 7, and so on. Okay, the examples Larry Wang gave 2 days ago didn't go unnoticed. Generating and alternating sequences of zeros and ones is really simple using 5. I took 20 of these values as well. 20 iota, I have a vector 0 to 19. 2 modulus, so I get a vector 0, 1, 0, 1, 0, 1, 0, 1. The first 20 powers of 2. It's a little bit more tricky, but not too tricky at all. I push a 2 and a 20 on the stack and perform a reshape. So I have a vector of 20 2s. Then I push a 20 on the stack and issue a iota. I get another vector 0 to 19. And all I do then is apply the power operator star star, and what I get are all powers of 2 from 0 to 19. The perfect numbers is, I'm really sorry, longer than the Perl 6 implementation, but we are working on this. That's the example we used for the NYT Prof speed up hackathon yesterday. The idea is quite simple too. What we are doing is we push the number in question on the stack and then generate a vector running from 1 to number -1 and divide modulus by all of these numbers, and what we get is a vector containing zeros and non-zero values. And we take this vector for a select operation after inverting it, and then applying quote plus reduce to get the sum of all the divisors of the number in question. And this program just outputs every perfect number between 1 and 500. Okay. That's a source code. Und you see all the perfect numbers between 1 and 500 are 6, 28, and 496. It takes 1.2 seconds to run this compared with seconds yesterday morning.
Well, it's actually faster than the two.
I really doubt this. Okay, let me come to my conclusion. What began as a toy project turned out to be a really usable project. Believe it or not, but at least 2 friends of mine are actively using it. One friend in France uses it as a customer's location to go through data and create simple statistics because he was used to use APL before. So we have at least one user for this interpreter.
Can't change anything now.
And another friend is doing real mathematics using 5 because his wife is doing her PhD in combinatorial mathematics, and 5 turns out to be really powerful if you have to perform combinatorial calculations. So what we are now going to do is we want to extract all of our array operations. Some array operations which I have not shown are really complex. For example, we have operations which allow to cut out an n-dimensional cube out of an n plus n-dimensional cube, which was horrible to write, or the reshape functions and so on. And we plan to extract these routines and put them on CPAM as a standalone module for array modifications. And of course, we are going to implement more and more of the still missing APL operators. I would like to thank Thomas Kratz, who did most of the coding, and our alpha users, who really had hard times getting through errors we have introduced. And I would like to thank all of you for interest in the application. Thank you very much. Any questions?
Is it pure Perl inside? Or
Yes, pure Perl.
Okay.
We don't need any special modules, so it even runs on OpenVMS, which was a prime goal. Yes?
Did you write your own parser, or did you make use of parse-rect-descent?
No, it's our own parser because it's so incredibly simple to parse a stack-oriented language. The only hard thing was to handle nested arrays in the parser. So if you have a look at the source code, will find a routine called transmogrify arrays. For all of you who know Calvin and Hobbes, there's the magic going on in the parser.
All right.
If we need to borrow all these operators that you've got there, in mostly borrowing them from APL,
yes.
if you could put them just into Perl without the 4th syntax, would you still end up programs similarly short?
Good question. I've been thinking about this also, and I'm pretty sure we will try this as soon as we have extracted our array manipulation routines into a standalone CPAN module.
Do you consider PDL as a backend implementation? It's very fast because we don't see, and it also can do arrays.
Not until now, but why not? Okay, if there are no more questions, thank you very much. Have a nice day.